Welcome back, everyone, to the Foundry by Forge College. I am absolutely thrilled to have you here for today's explainer. You know, in our previous lesson, we officially wrapped up and submitted the research paper, which means the purely theoretical phase, yeah, that's completely behind us. Now it's time to unroll the engineering blueprints and get our hands dirty. Today, we're focusing on a topic that literally has the entire Web3 space buzzing: Firedancer's role in the Solana network. We're going to trace out the exact schematics of this incredible piece of technology, and to match that vibe, we'll be looking at everything through these beautiful, minimalist patent-style diagrams.
Okay, let's dive right into this master blueprint. Our agenda today covers from research to reality, the Firedancer blueprint, pipelines and orchestras, the deployment workflow, and finally, beyond the magic box.
Starting with Section 1, from research to reality, let's see how we build this thing. So, we're taking all those theoretical network efficiency concepts you've been learning about and applying them directly to a real-world construction site. Because, hey, it's one thing to talk about efficiency in an academic paper, right? But it's another thing entirely to see how it operates under the crushing weight of live network traffic. So, what exactly is Firedancer? Let's define it clearly. The Firedancer validator is an alternative, plug-compatible validator implementation for Solana. Its entire focus, its whole reason for existing, is optimizing transaction pipelines and validator resource efficiency. Now, that term plug-compatible is doing some heavy lifting there. What it means is that on the outside, Firedancer speaks the exact same protocol language. It processes the very same proof of history ordered entries, validates signatures, and applies state transitions just like any standard node. But the moment you look under the hood, its internal architecture is fundamentally different. It's kind of like taking a standard car frame, keeping the exact same steering wheel and pedals, but dropping an incredibly fine-tuned racing engine inside. To really grasp why this is such a game changer, we have to contrast the standard canonical validator design with Firedancer's specific approach. In some of our recent modules, you examined Cloudbreak storage, which is Solana's way of handling massive data reads and writes. You also learned about proof of history, the internal clock that serializes time for deterministic ordering. Well, those two mechanisms push validators to their absolute limits. The standard design handles this well, for sure, but it comes with standard resource usage and latency. Firedancer totally flips the script. By fundamentally rewriting how data flows through the node, Firedancer actually achieves a significantly lower per-transaction CPU cost and a much, much higher sustained throughput. It's explicitly engineered to relieve those exact pressure points created by Cloudbreak and proof of history.
Moving on to Section 2, the Firedancer blueprint. Time to look at the internal mechanics.
Go ahead and put on your lead engineer hard hat for a second, because we're looking directly at the validator's internal mechanics now. To really wrap our heads around Firedancer, you gotta break it down into 3 interacting subsystems. First up, we have ingress and networking. This system is just completely obsessed with minimizing copy overhead and avoiding serialization bottlenecks. It literally wants data off the wire and into memory instantly. Second, we have the processing pipeline. This relies on fine-grained parallelism across independent transactions. Now, aggressive parallelism is fantastic for raw speed, until you realize it requires incredibly strict coordination to prevent total chaos and keep the deterministic execution order intact. It's a massive balancing act. And third, state management. This subsystem interacts with Cloudbreak-style storage with minimal blocking I/O. What does that mean in plain English? It means it tries its absolute hardest to never, ever stand around waiting for data to be written or read.
Now, what's genuinely fascinating here is how these abstract engineering choices translate into hard, measurable realities. Check out the optimized processing pipeline. For you, the operator, that directly means lower per-slot CPU cycles. For the network as a whole, higher sustained throughput. What about that fine-grained parallelism we just talked about? Well, for the operator, you get vastly better multi-core utilization. And for the network, massively improved aggregate throughput. Even the memory strategy changes your storage profiles and snapshot frequencies, which impacts how fast a peer can bootstrap and sync state. Whenever you evaluate Firedancer, you always have to separate the internal architecture from these observable metrics. The code itself might change in future updates, but these operational realities are what you'll constantly rely on.
All right, Section 3, pipelines and orchestras. Let's build some mental models.
Understanding the raw metrics is great, but to truly master this technology, we need the right mental framework. This is exactly how the best node operators visualize the system. You see, the core challenge of any validator is balancing raw throughput optimization against strict deterministic ordering. Think of a validator as a giant factory production line, a pipeline. You've got stages: ingress, verify, execute, commit, snapshot. And the slowest stage limits your entire factory's output. Obviously, you want massive throughput, but simultaneously, you have to imagine an orchestra.
Every single node in the network is a musician, and proof of history is the conductor. Every musician has to play the exact same notes in the exact same deterministic sequence, or else the ledger falls entirely out of sync. So you need the raw, blistering speed of the factory pipeline combined with the precise, synchronized timing of the orchestra.
And this brings us to a brilliant way of understanding conservative parallelism. Think of parallelism like opening multiple checkout lanes at a grocery store. Opening 10 lanes massively speeds up all those simple shoppers who are just buying a single apple, right? But the second you get customers with massive complicated orders who need price checks across 3 different departments, you suddenly need a manager to step in and coordinate everything, otherwise the entire front of the store stalls out. In Solana's architecture, those simple shoppers are independent transactions. The large orders are smart contract-heavy workloads that touch multiple cross-account dependencies. Firedancer is unbelievably fast, but if there's heavy contention across accounts, that parallelism has to be carefully managed to prevent the whole system from stalling.
So when you're evaluating Firedancer for your own setup, I highly recommend using a 3-layer thinking framework. Layer 1 is your per-node capacity. So if Firedancer drops your CPU usage from 20% down to 12%, that is a clear Layer 1 effect. Layer 2 focuses on cluster behavior. How does this specific node interact with the rest of the network when it comes to gossip and replication? And finally, Layer 3 is your operational lifecycle. How long does it actually take this node to restart? What's the snapshot cadence? You've got to evaluate Firedancer's impact across all 3 of these distinct operational levels to really understand its true footprint.
Moving right along to Section 4, the deployment workflow. Let's talk about a safe live launch.
How do we actually launch this safely into a live environment? This transitions us perfectly from our theoretical models right down to the physical construction site. Here's your essential 5-step roadmap for deployment. Step 1, characterize your workload. Are you read-heavy or write-heavy? Step 2, run controlled benchmarks. You have to treat your performance hypotheses as actual experiments. Step 3, decide your hardware sizing and placement based purely on those benchmarks. Step 4, design strict monitoring and rollback procedures. And Step 5, capture post-deployment lessons so you can close the loop. If you follow this process to the letter, you prevent catastrophic surprises when you hit the main net.
Let's zoom in on Step 2 for just a second. Because listen, you cannot just plug Firedancer in, cross your fingers, and hope for the best. You absolutely must instrument specific metrics during your controlled benchmarks. We're talking about watching your per slot processing time, your CPU utilization per core, your I/O wait time, snapshot generation time, and RPC latency. I know, it's a total alphabet soup of metrics, but these exact numbers are what you'll use for your capacity planning. You need to see exactly where and how Firedancer diverges from your baseline validator. Without this data, you are flying completely blind. And once you actually have those metrics, you gotta define concrete acceptance criteria. You need a strict, non-negotiable pass-fail threshold before you ever scale out to a consensus-critical role. For example, you might set a rule like, we will only proceed if the median slot processing time remains within 10% of our baseline. You plan a very incremental rollout. Maybe start with a non-critical canary node, which is basically a test dummy, and validate these metrics under production-like load. This methodical, strictly metric-driven approach, that is exactly what separates the professionals from the amateurs in Web3 engineering.
Which brings us to our final section, beyond the magic box. It's time to talk trade-offs.
Let's take a minute to shatter a pretty common myth in the blockchain space whenever a new tech drops. I want to be incredibly clear here. Firedancer is an absolute marvel of engineering. It truly is. But it is not a magic box that solves all your problems instantly without any trade-offs. What it actually is an alternate implementation that shifts pressure points. Think about it for a second. If Firedancer brilliantly optimizes your processing pipeline and your CPU usage suddenly plummets, well, your node is going to try to process data much, much faster. And what happens then? Suddenly, your storage I/O or your network bandwidth might become the new bottleneck. A lower CPU cost might simply reveal that your hard drives can't even keep up with the new blisteringly fast pace. You always have to validate the entire system, not just one isolated component. So I'll leave you with this thought. If Firedancer is the rocket engine, are your current benchmarks actually capable of measuring its speed without completely blowing out the dashboard? Next time, we're diving deep into performance metrics and signals, where we'll learn exactly how to interpret the numbers you gather from these real-world deployments. If you've enjoyed breaking down these engineering schematics with me today, there is so much more to explore. Head over to forge.college to dive deeper into the subject, check out our other courses, and continue your Web3 learning journey. I've been your host for this explainer. Keep building and keep learning.